Alright, continuing with this series of videos, I don't know, watching some physics lectures and providing alternative explanations where necessary. Unfortunately, this concept isn't something I disagree with fundamentally. I would just point out that stepper motors are, the idea of recognizing that pushing from one place, like say with a tether ball, and you just hit it where you're standing. Well, you could get a lot more out of it if you could move you to different positions and keep hitting it all the way around the circle instead of just once. And that's kind of this idea. And yes, perfectly agreeable in a lot of respects. Do it where you can. Such.
In 2 and 3 are down by a factor of 2. You can check that for you. During my lecture, I went a little bit too fast over the part that is coming up now. So I'm going to redo it a little slower to make it more clear. When the current through loop 1 reaches a maximum, let's say then that the magnetic field due to loop 1 is in this direction. The current through this one and the current through this loop are 2 times smaller. You may want to check that. But it just so happens that the vectorial sum of the magnetic field produced by loop number 2 and by loop number 3 also happen to be in this direction. So the net magnetic field is in this direction. Let's now look 1/3 of a period later in time. Now the current in loop number 2 reaches a maximum. So its magnetic field is now in this direction. And you guessed it, of course, that it just so happens that the vectorial sum of the magnetic field produced by the other 2 loops is now also in this direction. And if we now look again 1/3 of a period later, when the current through loop number 3 reaches a maximum, then the magnetic field will be in this direction, and the vectorial sum of the magnetic field of the other 2 loops will also be in this direction. And look now what has happened.
The point of these directions is just that this one would be a north and south kind of idea. You can think of it in that respect. But obviously the current or the magnetism is going opposite of this directional arrow. It's in another direction. But the point is the pushing force. And substantially that's what's running the motor, is the push of the opposite magnet.
In one complete period, the magnetic field started out like this. 1/3 of a period later, it was like this. And 1/3 of a period later, it was like this. So what we have created is now a rotating magnetic field. And it rotates in one period, all the way around, 360 degrees. Okay, let's now go back to my original lecture.
So it doesn't really rotate. The idea is that it's going in steps, and so it's not kind of rotating in any way. It's just picking up. This one does the work, and then this one does the work, and then the other one does the work at the right time. But it's not really rotating.
Well, it rotates once around in the period of your alternating current. If that is a 60 Hertz current, then it will rotate around the 60 Hertz, 60 times per second. And so if we put a magnet in here, then this magnet will want to go around, wants to follow this rotating magnetic field. And
keeps trying to flip. So the magnetic field is being created that's saying north-south, and it's saying I want to be north-south, south-north. So it keeps trying to flip. The way it can flip is to turn. So it keeps turning.
We call that a synchronous motor. So the rotor of such a synchronous motor itself would be a magnet, and it would rotate around with the frequency of your alternating current. But you need a 3-phase current for that.
So yeah, so now they use stepper motors. I think they did back when he was around, which even take advantage of more coils and just use electronics to move the current from each coil. So, they digitized it in a sense.
So that the magnetic field rotates. I can also place in here, this is again horizontal surface. You have it here. I'm going to do it right here. Here are those crazy loops with the 3-phase current. We can also put in here conducting sphere, or in my case I will use a conducting egg. And when the magnetic field rotates around, there is a continuous magnetic flux change with the surface of that conducting sphere or egg, and so it's going to run eddy currents. Now if you have an eddy current going around and you have a magnetic field, then the magnetic field and the eddy current will cause a torque.
So I'll say it again, the eddy current is irrelevant. What's really happening is the paramagnetic material is getting charged, essentially, and becoming, creating magnetic monopoles in positions that create magnetic dipoles, and it's just creating a opposite magnet, and things happen from there.
On the current. In a similar way, when we discussed earlier the idea of a motor that you are going to build,
it's not an opposite one. I meant to say it's the same magnetic orientation, which means it's repulsive.
There was a magnetic field, and there was a current, and that caused a torque. In the same way, you get a torque on the eddy current. And so it starts to torque up this conducting sphere. And all the time there will be eddy current, because the magnetic field keeps going around. And so you're going to get a torque which will always be in the same direction, and this conducting object will now start to rotate, and we call that an induction motor. Induction motors have no brushes. How fast the induction motor will go depends on the conducting object. If it is a sphere, it will probably come very close to 60 Hertz, because a sphere has many possibilities for eddy currents to run around. Whereas if you take a ring, and we will try that, if you try to spin a ring in a rotating magnetic field, then of course the various paths that are available for eddy currents are very limited. You can only go around in the ring. Many of the stationary tools that you find in people's workshops and in the basements are induction motors. Table saw and drill presses, also electric grass mowers, are induction motors. I want to demonstrate now to you what three-phase currents can do. And the first thing I'm going to do is show you that that unit that we have here, which are the coils that I described, through which we're going to run the three-phase current. Let's get my lights right. There you see it. Coils are wound in a very strange way. After class you can come a little closer. And so in here you would have a rotating magnetic field. We use 60 Hertz. It rotates around 60 times per second. And the first thing I'm going to do is something wild. A little bit in style, I suppose. I will put on top there a cardboard cover with little magnets. They're randomly oriented. There's no way that they can ever rotate. These are these little magnets, flat, a lot of friction. If I expose them to a rotating magnetic field, then they will go nuts. I told you they were going nuts. You're not supposed to show this to students, but... Oh.
Well, whatever. Obviously they were starting to stick to each other and become a bar magnet, and then the bar magnet would start to spin, so not so nutty.
Okay. Now here I have a conducting egg. And this now has ample possibilities for eddy currents to flow. And so now if I give these coils the right current, a three-phase current, it's spun up, the magnetic field acts on the eddy currents, and it starts to spin. And I have actually tried to measure the rotation rate. It's only a little bit under 3600 RPM. 3600 RPM would be 60 Hertz. It's very close to that. If I spin this object in the direction in which the magnetic field is not rotating, then it says, sorry, no way. It just reverses, because the magnetic field is going to slave it in the direction that it wants it to go. So you're looking there at an induction motor. I have here a ring. Now a ring doesn't have as many possibilities for eddy currents to run. It could only go around like this or like this, right? But I can still make it spin probably if I do the right thing. First of all, I have to rotate it in the right direction.
So it obviously is cutting the surfaces down, right? So, you know, there's a lot less to magnetize. Therefore, the effect is weak.
Direction, which would be this one, I think. There it goes. It doesn't go anywhere nearly as fast as the egg because of the restrictive path of the eddy currents. When it rotates, it's trying to follow that magnetic field to the best it can, but its abilities are very limited. And needless to say, if I try to spin it in the wrong direction, that of course it will stop, and it has no way, like the egg, to reverse its direction because of its peculiar geometry.
Yes, it doesn't have a round surface, so it can't pop back up like a weeble or something. It can't wobble and not fall down.
I owe you an explanation to the secret top, if you haven't found one yourself yet. Let me first come to a simple conclusion. And all of you must have come to that conclusion.
Right.
That top.
So this was the thing that was in the one video I didn't play. That was the pre-test video where he spun this little top, and obviously it was a gimmick because the top just kept spinning and spinning and spinning. And yes, little mind teaser.
When I showed it to you during my exam review, was spinning for more than an hour. In fact, it was spinning the next day. Energy has to come from somewhere. And so the only conclusion that you could have drawn that the energy came from inside the box, there must be something inside the box. Clearly, there must be a battery in that box. And there is. But it doesn't tell you how it works yet. And I can assure you, I can admit that it took me quite a while before I fully understand how it works. And I want to explain that to you, and then I will demonstrate it to you again. Remember what it looks like. In the top itself is a magnet. So here is the top. Let's say this is north and this is south, and this is that top. We're rotating it, we're spinning it. Inside the box, right at the center of the box, is a solenoid. A switch and a 9-volt battery. Inside this solenoid is also a little bit of iron. We have not discussed that in our course. It's not important for the explanation. You'll later understand why there's also some iron in here. It makes the magnetic field so it's a little stronger. This is right at the center of the little platform on which I was running this, which is a concave platform. And here is a little plastic notch, so when the top hits it, it bounces off. Imagine for now that it's rotating in such a way that the North Pole is approaching that solenoid, coming in from above. What's going to happen now, in this solenoid, in this coil, you are changing the magnetic flux through the surface of this coil, and so you're introducing an induced EMF, an induced current. And this current...
So it works both ways. So that's what the core allows, is for another paramagnetic response of the core becomes magnetized, which means the coil picks up that magnetism as electricity and sends a little electric signal to a transistor, which is the switch, and the switch says power on, and then it sends back an even stronger magnetic field.
Is sensed by a transistor, which I have not put in here. And the transistor throws this switch, and now sucks energy out of the battery, and runs current, very high current, through this coil, such that the top becomes the south pole. Remember, if you have a coil, and you run current through here, that you get a magnetic field like so. In this case, this would be north pole, and this would be south pole. If you reverse the current, then this is south and this is north. That magnetic field that comes out there is fanning out in all directions, three-dimensionally. It's going like this, and it's fanning out like this. So when it approaches this coil, there is a change in magnetic flux, and this becomes a south pole. The north pole is being attracted by the south pole. I make you look at this from above now. Here is the top seen from above, so it's spinning in this direction. And let's say here is this coil. This is the north pole, and this is the south pole. And I just discussed with you that the current that's going to flow from the battery will make this a south pole. The current can only flow in that coil in one direction. That's just the way it's designed. So whenever the current goes, it's always this becomes a south pole. The north pole is being attracted by the south pole. So notice it's going to be torqued up. So far, so good.
It's going to be torqued down. So I don't know why he said torqued up, but whatever. It's going to be pulled down, which means it's going to give it a little extra energy.
A little later in time, looking from above, the north pole will be here, and the south pole will be there. It has rotated a little bit further. And the coil is here. So now the North Pole is leaving. It's receding. It's not approaching, it's receding. If this were to remain the South Pole, that would be disastrous because South Pole and North Pole would attract each other. You don't want that. Well, the transistor senses that the EMF in the coil reverses direction. It has to reverse direction because if the North Pole comes in, the EMF is in one direction, but when the North Pole leaves, the EMF, of course, goes in the other direction. You get a reversal. And
right, so I think he's wrong in how he's describing how this works. I don't think it bothers sensing the North Pole leaving. It just does a pulse of magnetism. It shoots a little bit of current for a millisecond, gives the North Pole a little tug, and it just waits again to turn on. It can't sense and push at the same time. You can sort of understand that if you're sending current through the coil and magnetizing it, it's no longer sensing very much. It's you know, it's not much of a sensor because it's pushing current. It can't really, the tiny bit of difference between the current it's pushing and the current created by the North Pole is going to be so slight that I don't believe the transistor will be detecting that. So I don't think that's happening. But just, I don't think so.
so what the transistor does, it opens the switch. And so there is no North Pole here, and there is no South Pole here. And so the thing starts to go around further. What happens now when the South Pole approaches that solenoid? Okay, here is the situation that the South Pole is now approaching. It's rotating in this direction.
Happens.
And here is the coil. South Pole is coming in. From Faraday's point of view, there is no difference between the North Pole receding or the South Pole approaching. You should be able to reason that for yourself. That's exactly the same thing. And so the transistor knows that indeed the current is still in the wrong direction. It keeps the switch open. It does nothing. So as the South...
They're obviously not the same thing, so you can just, just point out for the sake of the argument, they're not exactly the same thing.
South Pole approaches, no current through this coil. Because remember, the current can only go in one direction. Can only make this a South Pole. It could have been designed in such a way that the current could go in both directions. They would have made it more expensive, just a matter of economy. So, nothing will happen here. But now, there comes a time that the South Pole is leaving, is receding. And so let us have here our coil. A South Pole receding is exactly the same for Mr. Faraday as a North Pole approaching. And so now the EMF is in the same direction in the coil as it was here. And so now the transistor says, "Youppi, that's fine. I close the switch and I'm going to run a current." And so this becomes the South Pole. South Pole and South Pole repel each other. So now the thing gets a kick again. So when the North Pole approaches, it pulls on the North Pole. And
so he's basically saying the same thing here in a different way. It's obviously pulling on the south and pulling on the north and rejecting the south in the first example. So, where he implied that it turns on and the South Pole is attracted, the North Pole is attracted to the south. Now he's saying the South Pole's repelled by the South Pole. Well, those are all the same. Those are the same thing. So it only does one action. It doesn't repel the South Pole and then in a separate action attract the North Pole. It's all in one action that both of those events take place. It forces the magnet to flip, essentially.
when the South Pole recedes, it pushes on the South Pole. And so it is an induction motor which is only powered half per full rotation. A very, very clever design. And I'm going to demonstrate it to you again. I want you to see that as this top approaches the center, that actually you can see it starting spinning up. It really gets its energy when it gets close to this coil. It also works, doesn't matter in which direction you spin it. That's also great. You can spin it clockwise or counterclockwise. Makes no difference. And so you're going to see that top here. I think, there it is. And this is probably the best way for you to see it. We have here this box in which there is this very simple circuit, very simple. And here is the top. There's a little bar magnet in it. I will try to spin it just a little bit to make you see that it actually spins up. It may not be so easy for you to see, but I can see, oh, you see it's really spinning up now. And then it loses through friction, rotation rates. It always comes back to the center because the surface is concave, and when it gets to the center, there it gets its kicks again. It gets spun up. And it can go on for as long as your battery lasts. It's about a few days. I can also rotate it counterclockwise. Not so easy, it's funny. Have you ever tried to rotate the top counterclockwise? It's very hard. I don't know why that is, maybe because I'm right-handed. I'll try. You see, I failed. Oh, this is a nice one. I gave it a teeny little spin. Doesn't like it. It stays near the center. Oh, doesn't like that. It has to be a little bit away from the center. Oh, I think I got it now. Oh no. Too optimistic. Isn't it strange that it's hard for a person to rotate something counterclockwise? Okay, I did it. Slowly coming in. Full friction now. And when it gets close to the center, there it gets its kicks. Now it's spinning up. Ah, you can really see it now. It's being spun up. You see that? Really spun up. I have another fantastic toy for you, which is also an induction motor. And that one, you're going to see there. I first want to explain to you how that one works. That's a real beauty. It is an induction motor that runs on a two-phase current. Here we have solenoid, this baby here, big one. And we're going to run 60 Hertz AC current through there. And here we have one, also going to run 60 Hertz AC through there. Here's the coil. This one is easy to show, the other one, very heavy. These two currents are 90 degrees out of phase. Not 120, but 90. So it's a two-phase current. So when the current is maximum through this one, it is zero through this one. When it's maximum through this one, it's zero through this one. Let's look at the moment that the current is maximum through this one. And let's say the magnetic field is in this direction, which is created by this coil. Then there is no current here. But 1/4 of a period later, this one has no current, but this one does. Let's assume that now the magnetic field from this one is in this direction. And so what you're going to see now is that again you have a rotating magnetic field which goes like so. And if I put in here a can, a paint can, we use a coffee can, it's right here.
I suppose you make it even 4-phase or whatever, you could just do the same thing on the opposite sides, and make it twice as good by having the opposite fields opposing each other. But again, it's just causing the magnet to flip, and in this case the paramagnetic material creates the opposition, creates the same magnetic field, which creates repulsion, which means it wants to flip.
Then at the surface of that can, so I will draw the can here, but it's really there. At the surface of that can, you're going to have eddy currents, because you have...
Alright, so again, you don't need the eddy currents. You're going to have the instantaneous reaction, which is when you hit it, when you pressurize its surface, the kind of pressure you're going to get back is reflective. That is, you're going to turn it into a mirror to the force you're imposing. It's going to reflect it back and forth, create a lot of repulsion, and that part of the can is one that gets out of there. It's one to go in one or two directions, and depending on what this other coil is, it's going to push it down rather than up, or clockwise rather than counterclockwise, depending on what field it's producing. But it's going to cause the can to spin, because it's going to keep wanting to flip away from the repulsive mirror charge.
Change of magnetic flux all the time, and these eddy currents with the magnetic field will cause a torque on this can, and the torque will always be in the same direction, and the thing is going to rotate. So it's another example of an induction motor. It's a very cute one, and I want to show it to you. And for that, you're going to see it there. Needless to say that the can is a very special can. Maxwell House coffee. Of course. Want to see that? Maxwell House. Alright, so let's see whether we can get this to run. There it goes. Nice example of an induction motor. And now I'm going to test you. I'm going to ask you what happens if I take this coil here, which I can do, and flip over from here to here.
It's going to change the direction in which it turns, because now you're creating the turning. You're saying to the magnet that your south pole can't go up, it has to go down. So you're just changing which way it turns.
Who thinks that nothing will happen? You're all afraid of me now, right? Who thinks that it will come to a grinding halt?
The way he has it now, it's basically making a south pole down. South pole down. It's alternating current, right? Well, I'm not gonna, won't hurt my brain.
Grinding halt. Who thinks that the direction of the motor will reverse? Good for you. It's clear that when I flip this one over, you can easily go through that for yourself.
Yeah, it's got to be DC current. Yeah, okay. DC at 60 cycles. That doesn't make sense. Yeah, so it's AC out of phase. Right, okay, so, well, anyway, so at the same phase location, the current way has it, the south pole is pointing down. That's why the can rotated clockwise.
That this magnetic field is then not rotating this way, but it's rotating that way. And so, clearly, the motor will reverse direction. I'm going to do that now. Watch it. So it's torquing now in the opposite direction. It's coming to a grinding halt. So you were right. The other people are also right. But now it's reversing direction. And you see, there it goes. Another striking example of an induction motor. Next lecture, Friday, I'm going to elevate a woman.
That sounds like a gimmick. Yeah. Yeah, you can see from the icon. Oh, yeah. And that was a special lecture. Anyway, so, sorry, a little bit too, like I said, not much to discuss, except it's the first thing that happens isn't that a current is created and the current creates a magnetic field. The first thing that happens is the atoms on the surface are being hit by a force. They react to being hit by charging, essentially pressurizing, and becoming themselves magnetic, or at least monopolarically magnetic, and creating a repulsive force. No eddy current required, and such. So till the next time, and such.